Hi everyone, today I will talk about ScaleHLS, achieving scalable high-level synthesis through MLIR. My name is Hanchen, and this is a collaboration work from UIUC and Georgia Tech. The motivation of this work is that we found large HLS designs which contain a large number of submodules or loops, and the complicated interconnections are difficult to be effectively optimized. The reason is that these large designs are hierarchical and are desired to be optimized at multiple abstraction levels. At the highest level, graph level, we can apply node fusion or insertion, and IP integration and extra. Then, at the loop level, all of the loop transformations are available, such as loop tiling and permutation, and local buffer insertion. Finally, we can insert directives, such as loop pipelining and array partitioning, to further fine-tune the performance and resource utilization of HLS designs. However, we found the existing HLS frameworks can only represent and optimize the HLS designs at one or two abstraction levels. Thus, they cannot open up a comprehensive design space to explore. Meanwhile, as the size of HLS design grows, the existing design space exploration algorithms are also not scalable. To address these problems, we propose ScaleHLS to handle large HLS designs through a multi-level representation and optimization methodology based on MLIR. First, let's take a look at the ScaleHLS framework. The input of the framework are programs described in high-level programming frameworks, such as Onyx and PyTorch, or general-purpose languages, such as C or C++. Currently, the output are synthesizable CPP code, or MLIR, which can be passed to external backends for generating RTL code. The inputs are first parsed into tensor-level operations in MLIR. At this level, we can easily analyze the dependencies between these tensor operations and apply graph optimization passes. Then, we lower the program into the loop level, represented with affine, standard, and SCF dialects in MLIR. After applying the loop optimization passes, we introduce a HLCPP dialect for representing the HL-specific structures and attributes for enabling the directive level optimizations. Finally, the optimized IR can be emitted as synthesizable CPP code by the HLCPP emitter. Meanwhile, we provide a rapid quality of result estimator for estimating the performance and resource utilization of the HLS designs inside of MLIR. By combining all graph, loop, and directive optimization passes and the quality of result estimator, we develop a DSE engine to automatically search for the Pareto frontier in the latency and area trade-off space. To evaluate the DSE engine, we adopted 6 computation kernels for experiments. The problem sizes are set to 4096. We can observe that the DSE engine achieves the speedup ranging from 40 times to more than 700 times compared to the baseline designs, which are only optimized by the regular LVM optimizations of Vivado HLS. This table also lists the optimization passes involved in the DSE, including loop perfection, remove variable bound, loop permutation, loop tiling, and loop pipelining. Meanwhile, the array partitioning strategies are also automatically selected and applied on the corresponding arrays based on the array accessing patterns. We also evaluated the capability of handling large and complicated designs. We adopted a MobileNet V2 PyTorch model as input and optimized it through the multi-level optimization methodology of ScaleHLS. In these two charts, D, Ln, and Gn denote directive, loop, and graph level optimizations. ScaleHLS supports to tune the level of loop and graph optimizations from 1 to 6. Thus, larger N indicates stronger optimizations. we can observe that by improving the optimization level, we can achieve a better performance while consuming more on-chip resources. Through this application study, we found all the 3 optimization contribute to the performance speedup, which demonstrates that our multi-level methodology is effective. This project will be open sourced in April, and the full-length paper with more details will also be available in this month. So stay tuned. Thanks.